So in chapter 3, we're going to shift gears again, okay? Chapter 1 was about how do we go about collecting data, right? So we talked all about data collection and how we can collect data correctly and so on, okay? Then in chapter 2, we had the data, we needed to organize it. So we organized our data into frequency distributions, relative frequency distributions, and then we constructed graphs so that we could kind of visually display that information and maybe look for patterns or be able to describe by using descriptions such as bell-shaped, uniform, and so on, okay? So in chapter 3, we're going to start looking at our first statistical calculations, okay? So we're going to start describing data numerically, okay? Now you may remember from chapter 1, we had a couple of terms. We had the term parameter and we had the term statistic, okay? A parameter was a numerical measure of a population. A statistic is a numerical measure of a sample. So we're going to start looking at these parameters and statistics that we can use to describe a set of data. So if you take a look here at the section 3.1 notes, I would expect section 3.1 is not going to have a whole lot of stuff here that you haven't worked with before. Now, what will be here that you probably haven't worked with before is some notation and some symbolism, okay? That will be new, probably, for most of you, unless you've taken statistics before. But the calculations themselves, I will bet almost anything that you have done at some point in your life. So what we're going to be looking at in section 3.1 are called measures of central tendency. So what in the world is a measure of central tendency? Well, if you'll remember when we had like a bell-shaped distribution, so a measure of central tendency would be like what would be the value in the center of that distribution. That's what we're talking about. So it's some kind of a calculation that's going to be describing the center of a set of data, so to speak. So the arithmetic mean of a variable is computed by adding all the values of the variable in a data set and dividing by the number of observations. So in other words, the arithmetic mean is what you would normally call an average. So the mean, or the arithmetic mean, we add up all the data values and we divide by the number of data values. So if we have 10 data values, you add up the 10 values and you divide by 10, that gives you the mean. Now, technically it's called an arithmetic mean, but most of the time we'll just use the word mean. So the word mean almost always is referring to the arithmetic mean. There are other kinds of means, but the most common is this arithmetic mean. So again, that's what you would normally call an average. Now, we will have a population mean and we will have a sample mean. So the population arithmetic mean is going to be denoted by this symbol right here. That symbol is the Greek letter mu. So mu is sort of like our letter M in the English alphabet, but again, it's Greek. So the population mean is a parameter. So it would be a measurement that is describing the entire population. Parameters are usually going to be denoted by Greek letters in statistics. So again, mu is representing mean. The way you write a mu, at least the way I do, is you start low, you come up to a point, curve back up, and then back down. I don't guess you could see that on the camera. Let me try this side. So you start low, come up, go back up, and go back down. There's mu, okay? And so you'll get very good at writing those because pretty much from now till the end of the semester, we will be using mu from this point onward. Anyway, the population mean, mu, is computed using all the individuals in a population. The population mean is a parameter, as I just said. The sample arithmetic mean is generally going to be denoted by x with a bar over it. And so we call that x bar. It is computed using sample data, and the sample mean is a statistic. So if we have a whole population of data, we will denote that mean with mu. If we have a sample of data, we will denote it with x bar. How do you calculate it? You add up all the data values and you divide by the number of data values. So you calculate it the same way, whether it's the whole population or whether it's a sample, we just denote it differently. Why do we need to denote it differently? Our ultimate goal in this class is to be able to use statistics to predict parameters. And so we have to know by our notation whether we're talking about a statistic or a parameter. Ultimately, we're going to use x bars to predict mu's, for example. Now, I will point out, normally we're going to use x with a bar over it. If I have more than one variable in a problem, let's say I have a variable represented by x and I have another variable represented by y, then I might use y with a bar over it, okay? So this would be the mean of the y variable. This would be the mean of the x variable, okay? So really the sample means notation is more about the bar than the actual letter that's being used. So we could have a z bar or a w bar or a t bar or what have you. In the same way, if we have a population and we're looking at multiple variables, so if we have an x variable and a y variable, we might denote the mean of the x variable by using mu with a subscripted x, so mu sub x, or we might have mu with a subscripted y. So this would be the population mean of the x variable, whereas this would be the population mean of the y variable. So we still use mu, we would just have a subscript to be able to distinguish between which variable we're talking about. While other types of means exist, the arithmetic mean is generally referred to simply as the mean. So technically we have the arithmetic mean, but usually we'll just call it the mean. Now, part of my job as the instructor of this class is to help you learn how to read mathematical notation. We're very good in math at taking something that's not really all that difficult and making it look horrible. And here's maybe our first example of that in this class. So take a look here. If x sub 1, x sub 2, and so on to x sub n are the n observations of a variable from a population, then the population mean, mu, is mu equals x sub 1 plus x sub 2 plus dot, 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 plus x sub n divided by n, which equals this mess. This is the definition of how we compute the population mean. Now, you all know how to calculate a mean. You just add up all the data values and you divide by the number of data values. So why does it look so horrible here? Well, let me help you decipher what this formula is actually saying. This is a formula for calculating a population mean. So first of all, you got to be familiar with the notation here. Mu, that's the population mean. That equals, now what's this x stuff? Well, from problem to problem, the values that you're going to be finding the mean for are going to differ. So we need to somehow have a generic way of describing the data values. So we're going to use the letter x. So the x with the subscripted 1 here, all that means is that's the first data value. And the x sub 2, that's the second data value. And x sub 3 would be the third data value. And x sub 4 would be the fourth data value, and so on. And if you have 1,000 data values, in other words, if your population size here is 1,000, then this would be X sub 1,000, and that would be the last data value. So you would add up all 1,000 data values and you would divide by 1,000. Only again, we don't know. We could have 1,000,000 data values instead of 1,000 data values. So we got to keep that generic. So that's why capital N represents the size of the population. So there are N data values. We're adding up all N of those data values, and then we're going to divide by N. So that's what this notation is talking about here. But mathematicians and statisticians are kind of lazy. We don't like writing too much. So when we get tired of writing something, we say, well, you know what, I'm tired of writing that. I'm going to make this symbol mean something. I mean, like, why does this mean to add? Someone got tired of writing add as a word, right? So they said, I'm going to use that symbol right there, and that's going to mean add. Why does this mean times? Someone got tired of writing times, and so they said, I'm going to make an X. That's going to represent times. And then someone thought that's too much work, so they said, you know what? Let's just use a dot instead. A dot means times. So anyway, it's the idea with these notations, okay? And then it looks hard, but it's really not always that hard. It's just learning to interpret what it's talking about. So again, this is too much to write. So we cut that down a little bit, right? So what's going on here? Well, this funky looking thing here kind of looks like a funky E. That is actually a Greek letter, and that is the Greek letter sigma. So in math, when you see a Greek letter sigma, and usually in science as well, sigma usually is going to represent sum. In math, it'll always represent sum. Okay, science, it'll always represent sum, S-U-M, sum, meaning to add. So anytime you see that Greek letter sigma with something behind it in math, that means you're adding. And what you're adding is what's behind it. So this is saying add up, and X sub I is representing the data values. We use a generic I, so that's like 1, 2, 3, 4, up to N, right? So we're going to add up all of the data values and then divide by N. So from this point onward in this class, anytime you see this sigma stands for sum. You're going to be adding up whatever it is that comes behind it. And that whatever comes behind it's usually going to be in the form of a variable. So the same kind of deal for a sample. If X sub 1, X sub 2, and so on up to X sub lowercase n are the lowercase n observations of a variable from a sample, then the sample mean X bar is X bar equals pretty much the same formula, X sub 1 plus X sub 2 and so on to X sub n. It's just technically a lowercase n since it's a sample. And we divide that by lowercase n, again, because it's the sample. Or again, that sigma means we're going to be adding up. What are we adding up? What comes behind it? X sub I is representing the data values. So add up all the data values, divide by the number of data values, and that gives us the mean. You have calculated means for ages, so I'm not concerned that you don't know how to find a mean. You're going to be able to calculate a mean. You just have to get familiar with the notations. Technically, if you are calculating the mean of a population, if you call it X bar, it's wrong. If it's for a population, it's not X bar, it's mu. And vice versa. If you're finding the mean of a sample and you call it mu, it's wrong. If you're finding the mean of a sample, it's going to be X bar or Y bar or T bar or whatever variable it is that you're dealing with. So use the notation correctly. So a quick example, the following data represent the number of emails received by Professor Gallagher on a random sample of 7 work days. So these are the number of emails that I received on these 7 work days. Compute the sample mean, round to the nearest 10th if necessary. So this is a sample, so we're going to calculate a sample mean, X bar. So X bar is just going to be what I get when I add up these 7 data values and divide by 7. So I'm going to take 82 plus 69 plus 73 plus 54 plus 75 plus 79 plus 66. Again, that's 7 different values that I'm adding up because I had 7 values in my sample. So I'm going to add that up and divide by 7. So if I bring in my calculator, 82 plus 69 plus 73 plus 54 plus 75 plus 79 plus 66, that is 498. So what I really have is 498 divided by 7. And if I take that 498 and divide by 7, that is approximately 71.1 if I round to 1 decimal place. So that is approximately 71.1. And if we include units, that would be emails. So for those 7 days, on average, I got 71.1 emails per day. What's a median? Well, the median is the variable, or the median of a variable, I should say, is the value that lies in the middle of the set of data if you put the data in ascending order. So in this class, we're going to use a capital M to represent median. The notations here for mu and X bar, those are pretty universal notations. So pretty much worldwide, anyone who finds a mean is going to use mu for a population mean and X bar for a sample mean. That's pretty universal notation. Any statistician is going to use those notations. For median, the letter M is not really universal. Our book uses M for mean, but lots of places will not. They'll just not even give it a symbol at all. They'll just call it the median, just so you know. So how do we go about finding a median? Well, with the mean, you calculate it, right? You find the average, so to speak. With the median, you don't really calculate it. You have to find it. So the way you find the median is, first of all, you have to rearrange the data and put it in order. And then you find what's the value in the middle. So I'm going to kind of skip to this example, and then I'm going to come back and talk about these steps. So Professor Gallagher's email data for 7 randomly selected workdays is repeated below. We want to find the median. So if I want to find the median for these data, the first thing that I have to do is put the data in ascending order. So my smallest data value in this case was 54. My next smallest data value is 66. So 66 is my next data value. My next data value is 69. And then 73. And then 75. And then 79. And then 82. So I have to put the data in order. And then I find what's in the middle. Well, if I have 7 data values, 73 is in the middle. So my median, again, our book will use a capital M for median, but lots of resources don't. Our median is 73. So how does it get harder? Well, the only way it gets harder is if we have a lot more data. So instead of 7 days, what if I had data for 70 days? Well, it's going to take a little more time to put the data in numerical order, and it would be easier to mess up finding what is the one that's in the middle. What about this example? Suppose a sample of 8 students have the following commute times in minutes from home to Lewis and Clark campus. So I have 8 data values, and these are the commute times. So someone drives 11 minutes, someone 26 minutes, someone 9 minutes, and so on. We're supposed to find the median. So again, I have to start by putting the data in order. So 5's the smallest, then 9, then 11, then 18, then 26, then 30, then 38, then 41. So there are our 8 data values in ascending order. Well, now, when we had 7 data values, 73 literally was in the middle. There's 3 values smaller than 73. There's 3 values larger than 73. But if I have 8 data values, well, the middle would be right here. We don't actually have a value in the middle. There isn't a middle, so to speak. So if we have an even number of data values, the way we calculate the median is we average the 2 middle values. So my median in this case is going to be the average of 18 and 26. So if I take 18 plus 26, that's 44. And 44 divided by 2 would be 22. So the median would be 22 for this set of data. Okay, we again just, when we have an even number of data, we average the 2 values in the middle. I do want to point out these steps just because I will use these on occasion. So if we're going to find the median of a data set, step 1, arrange the data in ascending order. Step 2, determine the number of observations that we have. Step 3, determine the observation in the middle of the data set. Okay, and then there's a couple of bullets here. So there isn't a formula for finding the median. There's no formula. You don't calculate the median, really. You find it. So there's no way that you can calculate to figure out what the median is. The only thing that you can really do is figure out where the median is, okay? And that's what these 2 bullets are about. So if I have an odd number of data values, like in this case, n was 7, if I will take the number of data values 7 plus 1 and divide by 2, that will tell me the position of the median. So if I take 7 plus 1, that's 8, and 8 divided by 2 is 4. So this gives me the position of the median. The median is the 4th data value once the data are in order. So that's what this is saying. If the number of observations is odd, then the median is the data value exactly in the middle of the data set. That is, the median is the observation that lies in the n plus 1 divided by 2 position. Now, again, if you have 7 data values, it's not hard to figure out what's in the middle. But if you have 70,000 data values, it's a little more challenging to figure out what's in the middle. So this n plus 1 divided by 2 will help you figure out where the median is. Not what it is, but where it is. But what if you have an even number of data values? Well, the author says this. If the number of observations is even, then the median is the mean of the 2 middle observations in the data set. So it's like what we did here, right? We averaged the 2 in the middle, okay? That is, the median is the mean of the observations that lie in the n divided by 2 position and the n divided by 2 plus 1 position, okay? So in other words, what the author is saying is if you've got an even number of data values, take the number of data values, 8 in this case, and divide by 2. That's 4. So you have the 4th data value and the 4 plus 1 equals 5 data values. So you average the 4th and 5th data values, which is what we did here, right? 18 was the 4th, 26 was the 5th, so we averaged those. Now I like trying to make things as simple as possible. So using like this formula, if it's an odd number of data, and this, if it's an even number of data, to me, I'm not crazy about that. I personally like using the same formula. So if you have an even number of data values, you could still take the 8 plus the 1 and divide by 2 using the same value that you do here. So that would be 9 divided by 2, And if you take 9 divided by 2, that would be 4.5. Well, 4.5, you don't really have a 4.5 position, but where would it be? It would be halfway between the 4th and the 5th data values. And so that one formula, n plus 1 divided by 2, will give you the position regardless of whether you have an odd or an even number of data.